Hello everyone, and welcome. I'm excited to kick off today's presentation on Python programming. This is our first slide, so I want to start by introducing the topic with a bit of enthusiasm. Today, we'll explore the fundamentals of Python, a powerful and versatile programming language. We'll cover key concepts, practical examples, and how you can get started with Python yourself. So, let's dive in and discover what makes Python such a popular choice among developers worldwide. Today, we're going to focus on understanding how lists, also known as arrays, are used to represent a collection of related data. We'll explore how these structures help us organize and manage information efficiently. I'll also introduce you to the various functions and methods available in Python that allow us to manipulate lists easily. By the end of this, you'll be able to write programs that effectively use lists to keep track of collections of data, making your code more flexible and powerful. So, let's dive into how lists can help us handle multiple pieces of information seamlessly within our programs. Today, we're going to explore how Python allows us to write programs that utilize lists and classes to organize complex data structures effectively. We'll look at how these tools help us manage and manipulate large amounts of information in a clear and structured way. Additionally, we'll delve into Python dictionaries, which are incredibly useful for storing collections that are non-sequential. This means we can access data quickly using keys, making our programs more efficient and easier to understand. These concepts are fundamental to writing versatile and powerful Python programs, and understanding them will help you build more organized and dynamic applications. Many programs often work with large collections of similar types of information. For example, think about words in a document or students enrolled in a course. It could also be data collected from an experiment or customers of a business. Even graphics objects drawn on the screen or cards in a deck are examples of collections we manage in programming. Understanding how to handle these collections efficiently is crucial, especially when we move into more advanced analysis or manipulation. So, as we progress, keep in mind that managing collections is a common task across many types of applications. This will set the foundation for the more detailed topics we're about to explore. And now, let's look at a simple example problem involving statistics to see these ideas in action. Let's review some code we wrote in Chapter 8. This is a simple program called average4, and its purpose is to calculate the average of a set of numbers. One of the key concepts here is the use of a sentinel loop, which allows us to keep asking for input until a specific condition is met, in this case, when the user presses enter on an empty line. You can see that we initialize the sum and count variables before starting the loop. Then, we prompt the user to enter a number, with the instruction that pressing enter will quit. Inside the while loop, as long as the input isn't empty, we convert the input string to a number using eval, add it to the total sum, and increment the count. We then ask for another input, repeating this process. Finally, after the loop ends, meaning the user has pressed enter without typing a number, we calculate and display the average by dividing the sum by the count. This example illustrates how sentinel-controlled loops work, which is a common pattern when processing an unspecified number of inputs. It ties into the overall theme of handling user input and performing calculations dynamically. Now, this program allows the user to enter a sequence of numbers, but interestingly, it doesn't keep track of each individual number entered. Instead, it only maintains a running total. This is a simple approach that works well for calculating the mean, but if we want to extend the program to compute other statistics like the median or standard deviation, we'll need to modify our strategy. For example, to find the median, we need to know the entire set of numbers, not just a total. The same goes for standard deviation, which depends on the individual data points. So, this sample problem introduces the idea of how we might build on a basic program to calculate more complex statistics, which is a key theme in data analysis and programming. The median is the data value that splits the data into equal-sized parts. For example, if we look at the data set 2, 4, 6, 9, 13, the median is 6. That's because there are 2 values greater than 6 and 2 values smaller than 6, so it sits right in the middle. One way to find the median is to store all the numbers, sort them in order, and then identify the middle value. This approach works well, especially when dealing with small data sets. In larger or more complex data sets, we might use different methods, but the core idea remains the same: finding the middle point. Understanding the median helps us get a sense of the center of our data, which is crucial in statistics and data analysis. The standard deviation is a way to measure how spread out the data is in relation to the mean. If most of our data points are close to the average, then the standard deviation will be small. On the other hand, if the data points are more dispersed and farther from the mean, the standard deviation will be larger. Essentially, the standard deviation acts like a yardstick that helps us understand how exceptional or typical our data is. It gives us a clear sense of the variability within the dataset, which is crucial in many statistical analyses and real-world applications. The standard deviation is a key measure of variability in our dataset. Here, we see the mean, which is the average of all data points. The symbol represents the ith data value, meaning any individual piece of data we're analyzing, and n is the total number of data values in our set. The expression inside the parentheses, which is the deviation of an individual item from the mean, shows how far that particular data point is from the average. When we square this deviation, it ensures all differences are positive and emphasizes larger deviations more strongly. This concept is fundamental because it gives us a sense of how spread out our data is around the mean. For example, a smaller standard deviation indicates that data points are clustered closely around the mean, while a larger one suggests more variability. In our upcoming example, we'll see how these ideas come together in a simple statistical problem, and how we can apply Python programming to calculate these measures efficiently. The numerator is the sum of these squared deviations across all the data points. Let's consider an example with the data set 2, 4, 6, 9, and 13. The mean of this data set is 6.8. Now, to find the numerator of the standard deviation, we need to calculate each deviation from the mean, square each of those deviations, and then add them all together. This step is crucial because it helps us measure how far each data point is from the average, giving us a sense of the data's overall variability. Understanding this process is fundamental because it lays the groundwork for calculating the standard deviation, which is a key measure of dispersion in our data. As you can see, calculating the standard deviation not only requires the mean, which can't be calculated until all the data is entered, but also each individual data element. We need some way to remember these values as they are entered. This is important because, without storing these individual data points, we won't be able to accurately compute the standard deviation. This highlights the need for an effective method to keep track of each piece of data during the process. So, in our next steps, we'll look at how to do just that, especially when working with programming tools like Python. So, here's the challenge. We need a way to store and manipulate an entire collection of numbers. Imagine trying to do that with just a bunch of individual variables. It's quickly going to become unmanageable. We don't know ahead of time how many numbers we'll need to work with, so that approach just doesn't work well. What we really need is a method to combine all these values into one single object. That way, we can handle, access, and modify the entire collection easily, rather than managing each number separately. This is where applying lists comes into play. Lists are perfect for grouping multiple items together, especially when dealing with an unknown or variable number of elements. They give us a flexible, organized way to store and work with collections of data, which is essential as our programs grow more complex. So, understanding how to use lists effectively is a key step in our journey into Python programming, helping us manage data more efficiently and making our code more powerful and easier to maintain. Let's talk about Python lists. They are ordered sequences of items, which means that the order of the elements is important and preserved. For example, imagine we have a sequence of numbers, which we can call S. We might write it as S equals S0, S1, S2, S3, and so on, up to Sn-1. This notation helps us understand that each item in the sequence has a specific position, or index. We can reference any specific value in the sequence using subscripts, like S0 for the first item, S1 for the second, and so forth. This concept is especially powerful because, in mathematics, using subscripts allows us to quickly and clearly describe computations over the items in a sequence. For instance, we can easily refer to sums, averages, or other operations by using these subscripted variables. When we move from lists to arrays in Python, the idea stays similar. Both are ordered collections of data. Understanding these fundamental concepts helps us write more effective programs, especially when handling sequences of data in a structured way. Let's look at how we can work with sequences in Python. Suppose the sequence is stored in a variable called S. To calculate the sum of all the items in this sequence, we can write a simple loop. First, we initialize a variable called sum to 0. Then, we use a for loop to iterate over the range of n, which is the length of the sequence. Inside the loop, we add each item Si to the sum. This pattern is very common across almost all programming languages, and it's often called working with an array or a list. The key idea here is that sequences like lists and arrays allow us to organize multiple items together and process them efficiently. Recognizing this structure is fundamental to writing effective algorithms and understanding how data is stored and manipulated in programming. So, understanding how to loop through sequences and perform operations like summing is a crucial skill, especially as we build more complex programs. A list or array is essentially a sequence of items, and we usually refer to the entire sequence with a single name. Like S, think of it as a container holding multiple elements. You can access individual items within that sequence by using indexing, which means specifying the position of the item, like Si. In many programming languages, arrays tend to be fixed in size. So, when you create an array, you need to define how many items it can hold right from the start. This is different from lists in Python, which are more flexible. Another important point is that arrays are typically homogeneous, meaning they can only hold one type of data at a time. For example, all numbers or all strings, but not a mix. This characteristic is useful because it allows for more efficient storage and processing. Understanding these key features helps us see how lists and arrays fit into the bigger picture of programming, especially in terms of data organization and access. Knowing when to use an array versus a list depends on whether you need fixed size and homogeneity or flexibility. Let's talk about Python lists. One of their most powerful features is that they are dynamic. This means they can grow or shrink as needed, giving us a lot of flexibility when managing data. You don't have to worry about predefining their size. They adapt on the fly. Another key point is that Python lists are heterogeneous. Unlike some languages that require all elements to be of the same type, a single list can hold different data types. So, you could have integers, strings, objects, all in one list. This ties into the idea that lists are mutable sequences. You can change their content, add, remove, or modify items after creation. And because they can hold arbitrary objects, they're incredibly versatile for various programming tasks. Now, connecting this to the overall theme of data structures, lists and arrays are fundamental tools. But Python lists, with their flexibility and ability to hold different types, often make them the go-to choice in many applications. Let's take a closer look at some fundamental list operations in Python, which are essential for effective programming. First, we have concatenation, represented as sec plus sec. This allows us to join two sequences together, creating a new combined sequence. Next is repetition, shown as sec times intexpr, which repeats a sequence a specified number of times, useful for generating repeated patterns or initializing lists. We also have indexing, written as sec with square brackets. This lets us access individual elements within a sequence by their position, which is crucial for data manipulation. Length, expressed as len/sec, tells us how many elements are in a sequence, helping us understand its size at any point. Slicing, or end, provides a way to extract a subset of the sequence, enabling us to work with specific portions of data. Then there's iteration, shown as for var in sec, which is the backbone of looping through sequences to perform repeated actions on each element. Lastly, membership testing, written as expr in sec, returns a Boolean indicating whether a particular element exists within the sequence. These list operations are fundamental tools that allow us to manipulate and analyze data efficiently, tying back to our overall theme of mastering Python for powerful programming. Now, except for the membership check, we've actually used these kinds of operations before when working with strings. The membership operation, in particular, is quite useful because it allows us to see if a certain value appears anywhere within a sequence. For example, if we have a list like this, LSD equals 1, 2, 3, 4, and we want to check if 3 is in that list, we can simply write 3 in LSD. And as you can see, that will return true, confirming that 3 is indeed present in the list. This is a powerful and straightforward way to test for the presence of an element, and it applies not just to lists, but to other sequences as well. It's a handy tool to keep in mind as we continue exploring list operations and their applications in Python programming. Let's take a closer look at the summing example we discussed earlier. Instead of writing out the process, we can represent it like this. We start with a variable called sum initialized to 0. Then, we go through each element in the list S, and for each one, we add its value to sum. This loop continues until all elements are processed, giving us the total sum at the end. Now, shifting gears a bit, I want to highlight an important difference between strings and lists in Python. Unlike strings, lists are mutable, which means we can change their contents after creation. For example, if we create a list like LSD with the elements 1, 2, 3, and 4, we can access the element at index 3 and see that it's 4. But we can also change that element to something else, like hello. After doing that, if we print LSD, it now shows the list with hello replacing the original 4. Similarly, we can change other elements, like replacing the element at index 2 with the number 7. The list updates immediately, reflecting these changes. This mutability is a key feature of lists that we'll explore further, especially as it allows us to modify data dynamically during program execution, which is essential for many real-world applications. So, understanding how lists work and their mutability opens up a lot of programming possibilities for us. Now, let's talk about creating lists with repeated items, which is a really useful feature in Python. The key idea here is the repetition operator, which allows us to generate lists containing multiple copies of the same element. For example, if we want a list with 50 zeros, we can simply write zeros equals 0 asterisk 50. This command creates a list with 50 zeros exactly. It's a powerful way to initialize lists when you need a large number of identical items, especially in cases like setting up default values or preparing data structures. Remember, this approach keeps your code clean and concise, making it easier to manage large data sets. Overall, understanding how to generate repeated items efficiently is an important part of mastering list operations in Python, and it fits into the broader theme of writing effective, streamlined code. Let's talk about how lists are often built up one piece at a time using the append method. In this example, we start with an empty list called nums. Then, we ask the user to input a number, which we store in the variable. As long as the number entered is non-negative, we add it to the list using the append method. After appending, we prompt the user again for another number. This process continues until the user enters a negative number, which stops the loop. The key idea here is that nums functions as an accumulator. It begins empty, and each time through the loop, a new value is added to it. This technique is very common when building lists dynamically based on user input or other data sources. It highlights how flexible and powerful list operations can be in Python, especially when you're gathering data piece by piece. Overall, this pattern is fundamental for managing collections of data efficiently in your programs. Let's take a closer look at some common list methods in Python. First, we have append x. This method adds an element x to the end of the list. It's a simple way to expand your list dynamically. Next is sort. This method sorts the list in order, and you can even pass a comparison function if you want custom sorting behavior. Then there's reverse, which simply reverses the order of the list elements. Moving on, index x returns the position of the first occurrence of x within the list, which is useful for locating items. The insert ix method allows you to insert an element, x, at a specific position, I, in the list. The count x method tells you how many times x appears in the list. And remove x deletes the first occurrence from the list, which is handy for cleaning up data. Lastly, pop I removes the element at index I and returns its value. This is especially useful when you need to both remove and access an item simultaneously. These methods form the core toolkit for manipulating lists in Python, and mastering them is essential as you build more complex programs. All right, let's walk through some common list operations in Python. First, we start with a list called LSD, which initially contains the numbers 3, 1, 4, 1, 5, and 9. We can add a new element like 2 using the append method. After appending, the list now includes that 2 at the end. Next, we can sort the list with the sort method, which arranges the numbers in ascending order. As you see, after sorting, the list becomes 1, 1, 2, 3, 4, 5, 9. Then, revering the list with reverse flips it around, so now it starts with 9 and ends with 1. We can find the position of a specific element, like 4, using the index method, which tells us it's at position 2. If we want to insert an element at a specific position, such as inserting the word hello at index 4, we use insert. Notice how hello appears at that position now. To count how many times a value appears, like 1, we use the count method. But be careful, note that in the code, there's a typo with an extras after ones. The correct way is LSD, count 1, which returns 2 because 1 appears twice. If we want to remove an element, say the first occurrence of 1, we use remove. The list updates accordingly, removing 1, 1. To remove an element at a specific index, like index 3, we use pop. In this case, it removes the element at position 3, which is 3, and returns it. The list then updates by removing that element. Throughout these operations, we see how flexible and powerful lists are in Python: adding, sorting, revering, searching, inserting, counting, and removing elements. These are fundamental tools that help us manipulate data efficiently as part of our broader programming tasks. Most of these methods don't return a value, meaning they modify the list directly rather than giving back a new one. This is an important point because it affects how we use these methods in our programs. Lists can grow by adding new items through appending, or they can shrink when we delete items. Speaking of deletion, we can remove individual items or even slices of items from a list using the del operator. This gives us a lot of control over list contents, which is really powerful when managing data dynamically in our code. Remember, these methods are essential tools for manipulating lists efficiently and effectively in Python. Let's look at this example to understand how the del statement works with lists. First, we start with my list containing the elements 34, 26, 0, and 10. When we execute del mylist1, we remove the element at index 1, which is 26. After this operation, becomes 34, 0, and 10. Now, here's an important point. The del statement isn't a method of the list itself. Instead, it's a built-in Python operation that can be used to delete items from a list, or even slices of a list. Next, when we do del mylist1, 3, we're deleting the slice from index 1 up to, but not including, index 3. In this case, that means removing the elements at positions 1 and 2, which are 0 and 10. After this operation, only 34 remains in the list. So the key takeaway here is that del allows us to delete individual elements or slices from a list efficiently. It's a powerful tool for managing list contents dynamically during your programming. Let's take a closer look at some basic list principles. A list is essentially a sequence of items stored as a single object. which means you can think of it as a container holding multiple elements. One of the powerful features of lists is that you can access individual items using indexing, which is like pointing to a specific position in the list. And if you want to work with a subset of the list, you can do that through slicing, which allows you to access a range of items. Another important point is that lists are mutable. This means you can change their contents after creation. You can replace individual items or even entire slices using assignment statements. This flexibility makes lists very versatile and a fundamental part of Python programming, especially when handling dynamic data. Understanding these principles is key because they underpin many operations you'll perform with lists throughout your coding journey. They help us manage and manipulate collections of data efficiently and effectively. Support a number of convenient and frequently used methods. Lists will grow and shrink as needed. List operations are fundamental in Python programming because they allow us to manage collections of data efficiently. These operations include adding, removing, or modifying items in a list, and they make working with data more flexible. As we work through more complex programs, you'll see how lists adapt dynamically, growing or shrinking depending on your needs. Understanding list operations is key to writing effective Python code, and it ties directly into the overall theme of making programming more intuitive and powerful. One way we can solve our statistics problem is to store the data in lists. By doing this, we can organize our data more efficiently and make it easier to perform calculations. Then, we could write a series of functions that take a list of numbers as input and calculate the mean, the standard deviation, and the median. This approach makes our code more modular and reusable. Let's go ahead and rewrite our earlier program to use lists for finding the mean, which will help us see how this method simplifies the process. This concept of using lists is really powerful because it connects directly to how we can handle larger datasets in a more manageable way. So, as we move forward, keep in mind that organizing data into lists is a key step in making our statistical calculations more flexible and scalable. All right, let's walk through how to create a function called getNumbers that gathers numbers from the user. We'll use what's called a sentinel loop to handle this process, which means we'll keep asking for input until a specific condition signals us to stop. To keep track of all the numbers entered, we'll use an empty list at the start. That way, we can keep adding each new number to this list as we go. Once the user indicates they're done entering values, the function will return the complete list. This approach highlights how lists can be very effective for collecting and managing multiple data points, which ties into our overall theme of working with data in Python. Let's take a closer look at this function called getNumbers. The purpose here is to gather a list of numbers from the user interactively. We start by initializing an empty list called nums, which will hold all the numbers the user enters. The key part of this code is the sentinel loop, which keeps asking the user for input until they decide to stop by just pressing enter. So we prompt the user with a message, enter a number, enter to quit. If they enter something, we convert that input from a string to a number using eval, and then append it to our list. The loop continues, repeatedly asking for more numbers, until the user hits enter without typing anything, which makes the condition xstr equals false, and the loop ends. Finally, the function returns the complete list of numbers. This setup is really efficient because with just a single line, data equals getNumbers. We can collect multiple inputs into a list, making it easy to perform statistical calculations or other analyses later on. It exemplifies how Python makes data collection straightforward, especially when working with lists and user input. Now, we need a function that will calculate the mean of the numbers in a list. The input for this function is a list of numbers, and the output is the mean of that list. The function is defined as defMean, taking a parameter called nums, which is our list of numbers. Inside the function, we initialize a variable called sum to 0 to hold the total sum of the numbers. Then, we use a for loop to go through each number in the list. For each number, we add it to our sum variable. This way, at the end of the loop, sum contains the total of all the numbers. Finally, we return the sum divided by the length of the list, which gives us the average or mean. This approach is straightforward and highlights a common pattern in programming, summing elements and then dividing by their count to find the mean. This function is a fundamental building block in statistics and data analysis, connecting well to our overall theme of working with lists and extracting meaningful insights from data. Now, the next function we're going to tackle is the standard deviation. To calculate the standard deviation accurately, we first need to know the mean of our data set. This raises an important question. Should we recalculate the mean inside the std_dev function each time we call it? Or would it be better to pass the mean as a parameter? This decision impacts both the efficiency and clarity of our code. If we have already calculated the mean elsewhere, passing it as a parameter can save us time, especially with large datasets. On the other hand, recalculating inside the function keeps things more self-contained, which can be simpler to manage in smaller programs. This choice ties into the overall theme of writing clean, efficient, and reusable code in Python. So, understanding when and how to handle these intermediate calculations is key as we build more complex statistical functions with lists. Recalculating the mean inside of std_dev is inefficient if the data set is large. Since our program is outputting both the mean and the standard deviation, let's compute the mean first and then pass it to std_dev as a parameter. This approach helps us avoid redundant calculations, making our code more efficient, especially with big data sets. Remember, when working with lists in Python, reusing already computed values can save a lot of processing time. This is a good example of how understanding the flow of data and optimizing calculations can improve overall performance in our statistical programs. It ties back to our overall theme of writing efficient, effective Python code for handling data. Let's walk through this Python function for calculating standard deviation. The function is named std_dev and it takes two parameters, nums, which is a list of numbers, and xbar, the mean of those numbers. First, we initialize a variable called sumDevSQ to 0. This variable will serve as our accumulator or running total for the squared deviations. Then, we use a for loop to go through each number in the list. For each number, we calculate the deviation by subtracting the number from the mean. We then square that deviation by multiplying it by itself. Next, we add this squared deviation to our accumulator, sumDevSQ. After the loop has processed all numbers, we compute the standard deviation by taking the square root of the total sum of squared deviations divided by the number of data points minus 1. This division by len, nums, minus 1 is important because it provides an unbiased estimate of the population's standard deviation, especially when working with a sample. So, in essence, the loop handles the summation of squared deviations, and the final return statement completes the calculation by applying the square root. This method highlights how Python can efficiently perform statistical calculations with simple loops and accumulators, making the process both clear and adaptable for various data analysis tasks. We don't have a simple formula to calculate the median, so we need to create an algorithm to find the middle value in a list. First, we have to arrange the numbers in ascending order, from smallest to largest. Once the list is sorted, the middle value will be the median. If the list has an odd number of items, that middle position is straightforward. But if the list has an even number of items, then the median is actually the average of the two middle values. This approach helps us understand how to find the median even when there isn't a direct formula, and it ties into our overall theme of working with data and statistics in Python. Let's walk through the pseudocode for finding the median in a list of numbers. First, you start by sorting the numbers in ascending order. This step is crucial because the median depends on the position of values within a sorted list. Once the list is sorted, you check whether the size of the data set is odd or even. If it's odd, the median is simply the middle value. That means the element at the index in the middle of the list. If the size is even, then the median is calculated by taking the average of the two middle values. These are the two central elements in the sorted list. Finally, the pseudocode returns the median value, which represents the central tendency of the data. This approach is fundamental in statistics and helps us understand the typical value within a dataset. It's a great example of how algorithms can be used to process and analyze data efficiently. Let's take a closer look at this Python function called median. The purpose here is to find the median value in a list of numbers. First, we start by sorting the list with nums sort. This is crucial because the median depends on the data being in order. Next, we determine the size of the list using len nums and store it in the variable size. Then, we calculate the middle position with size2, which gives us the index of the middle element. Now, here's where it gets interesting. We check if the size of the list is even, using size %2 == 0. If it is, the median is actually the average of the two middle numbers, which are at positions midpose and midpose, 1. We add those two values together and divide by 2. If the size is odd, then the median is simply the middle element at index midpose. Finally, we return the calculated median. This function highlights how sorting and conditional logic work together to find the median efficiently. It's a great example of combining basic programming concepts to solve a common statistical problem. So with these functions in place, the main program itself becomes quite straightforward. What we're doing here is defining a main function that serves as the core of the program. First, we print a message to let the user know what the program does, that it computes the mean, median, and standard deviation of a dataset. Next, we call getNumbers to gather our data, which is typically a list of numbers. Then we calculate the mean by passing that data into the mean function and store the result in xbar. We do the same for the standard deviation, calling stddev, and passing in the data along with the mean we just computed, storing that in std. For the median, we call median with our data and save the result in med. Finally, we print out the results in a clear way, showing the mean, standard deviation, and median. This structure keeps the main program simple and easy to follow, highlighting how these functions work together to analyze the data. It's a great example of how modular programming helps make complex tasks manageable. Alright, so here on slide 39, we're talking about how statistical analysis routines can be really useful down the line. To make our code more flexible and reusable, we add a special construct. If name == main. This line essentially tells Python to run the main function only when we execute the script directly, not when we import it as a module. This is a key point because it allows us to write code that can serve dual purposes, both as a standalone program and as a module that others can import and use. It's a common practice in Python programming that enhances modularity and organization. Now, connecting this to our overall theme, it shows how we can prepare our statistical routines to be more adaptable. By structuring our code this way, we make it easier to incorporate lists for data handling and analysis, which is what we'll be exploring further. So, in essence, this approach helps us build more robust, reusable, and organized programs, crucial skills as we get into more complex data analysis tasks. All of the list examples we've looked at so far have involved simple data types like numbers and strings. But did you know that lists in Python can also store more complex data types? For example, in Chapter 10, we saw how we could use lists to hold student information. This means we can have a list of objects, which are essentially instances of classes or more structured data types. Using lists of objects allows us to organize and manage more detailed data, making our programs more powerful and flexible. So, understanding how to work with lists of objects is a key step in writing more advanced Python code that can handle real-world data more effectively. Now, our grade processing program reads through a file containing student grade information. It then identifies and prints out the details of the student with the highest GPA. This highlights an important operation we often perform on data like this: sorting. Sorting can be done in different ways, such as alphabetically by student name, by credit hours, or by GPA. Understanding how to organize data efficiently is key in programming, especially when working with lists of objects like student records. By mastering sorting techniques, we can make our programs more powerful and versatile in handling real-world data. All right, let's walk through how we can write a program to sort students based on their GPA, using the student class we discussed in the last chapter. First, we'll get the name of the input file from the user. This allows us to read student information dynamically, no hard coding needed. Once we have that, we'll read all the student data into a list of student objects. This makes it easy to manipulate and sort the data later on. Next, we'll sort this list by GPA, which is a key point because it demonstrates working with object attributes and sorting techniques. After sorting, we'll ask the user for the output file name, so we know where to save the sorted data. Finally, we'll write the student information from our sorted list into that file. This process ties together reading, manipulating, and writing data, all centered around working with lists of objects, an important concept in Python programming. Let's begin with the file processing. The following code reads through the data file and creates a list of students. First, we define a function called readStudents that takes a file name as its parameter. Inside the function, we open the file in read mode and assign it to the variable info. Then, we initialize an empty list called students. As we loop through each line in the file, we use the makeStudent function to convert each line into a student object, which we then append to our students list. After processing all lines, we close the file to free up resources. Finally, we return the list of students. Now, it's important to note that we're using the makeStudent function from the GPA program, so we need to remember to import it beforehand. This process is a fundamental part of handling data files in Python, especially when working with objects like students. It connects to our overall theme of data processing and object management in programming. Now, let's look at how we can write a function to save our list of students back to a file. The idea here is that each line in the file will represent one student, and it will include 3 pieces of information: their name, their credit hours, and their quality points. These will be separated by tabs to keep everything organized and easy to read later on. We'll define a function called writeStudents, which takes 2 parameters: the list of student objects and the file name where we want to save the data. Inside the function, we open the specified file in write mode. Then, we loop through each student in the list. For each student, we retrieve their name, hours, and quality points using getter methods, and we print these values to the file, separating them with tabs. Finally, after writing all the students, we close the file to ensure everything is saved properly. This approach makes it straightforward to store and later retrieve student data, which is essential for managing records efficiently in Python programming. Now, using the functions readStudents and writeStudents, we can easily convert our data file into a list of student objects. Once we've got that list, we can modify it as needed and then write it back to a file. The key step here is sorting these student records by GPA, which is often a crucial part of managing student data. In our earlier statistics program, we used the sort method to organize a list of numbers. But now, the question is, how does Python handle sorting lists of objects, like our student records? This is where understanding how Python sorts objects becomes really important. It's not just about numbers anymore. It's about defining the criteria for comparison, like GPA in our case. So the main point to remember is that, when sorting objects, we need to specify how Python should compare them. And that connects directly to our overall goal of organizing and analyzing student data efficiently. To make sorting work with our objects, we need to tell the sort function how to compare them. We can do this by supplying a function that produces a key for each object, using the syntax list, sort key equals sumfunc. For example, if we want to sort students by GPA, we need a function that takes a student object as a parameter and returns that student's GPA. This way, the sort method knows to compare students based on their GPA, rather than their default ordering or object memory addresses. Using keys gives us a flexible way to define custom sorting criteria for any kind of object in our programs. Now let's look at how we can sort a list of objects using a key function. Here, we've defined a simple function called useGPA, which takes a student object and returns its GPA by calling a student, GPA. This function acts as a key extractor. We can then pass this function to the sort method as the key parameter. When we do that, the list will be sorted based on the GPAs of the students. This approach is very flexible because it allows us to specify exactly what attribute or property of the objects we want to sort by. Remember, this is a common pattern when working with lists of objects in Python. It keeps our code clean and makes sorting based on complex criteria straightforward. All right, let's look at this line of code. Data, sort, key equals use GPA. Notice that we didn't put parentheses after use GPA. That's a crucial point. We're not calling the function here, but instead, we're passing the function itself to the sort method. This allows sort to use our use GPA function as a key to determine how to order the elements in the list. It's like giving sort a little helper function to tell it what part of each object to look at when sorting. Remember, if we put parentheses, it would execute use GPA immediately and send its result, which isn't what we want here. This concept is fundamental when working with functions as arguments, passing the function itself, not calling it. It's a common pattern in Python for customizing how sorting or other operations work on complex data structures. Actually, defining use GPA was unnecessary. The GPA method in the student class is a function that takes a student as a parameter, which we refer to as self, and it returns that student's GPA. This means that instead of writing a separate function outside the class, we can directly call this method on objects or classes. For example, if we want to sort a list of student objects based on their GPA, we can simply use datasort and specify key equals student, GPA. This makes our code cleaner and more object-oriented. When working with lists of objects, it's important to understand that we can sort or manipulate them based on their attributes or methods, which encapsulate data and behaviors neatly within the class. Connecting this to the overall theme, it highlights how defining methods inside classes allows for more intuitive and efficient data handling, especially when dealing with collections of objects. Let's walk through the main parts of this program. First, we define a main function that serves as the starting point. Inside it, we print a message to explain that the program sorts student grade information by GPA. Next, we ask the user to enter the name of the data file containing the student records. We then call the readStudents function, passing in that file name, to load the data into a list of student objects. After that, we sort this list by GPA using the sort method and specifying student, GPA as the key. Once sorted, we prompt the user again to enter a name for the output file where the sorted data will be saved. We then call writeStudents, passing in the sorted data and the output file name to write the information to a file. Finally, we print a confirmation message indicating that the data has been written successfully. At the bottom, the usual if name equals main line ensures that main runs when the script is executed directly. This structure makes the program user-friendly and modular, emphasizing clear separation of reading, sorting, and writing data, an important concept when working with objects and files in Python. In the DieView class from Chapter 10, each object keeps track of 7 circles representing the position of pips on the face of the die. Previously, we used specific instance variables like pip1, pip2, pip3, and so on to manage each individual pip. While this worked, it wasn't the most efficient approach, especially as the number of pips or faces increases. That's where designing with lists and classes comes into play. Instead of having separate variables for each pip, we can store all of them in a list. This makes the code more flexible and easier to manage. For example, if we need to update or access all the pips, we can do so with a simple loop through the list rather than multiple individual references. Using lists allows us to write cleaner, more scalable code, which aligns with the overall theme of improving our programming practices. It also highlights the power of classes in organizing related data. Grouping the pips together as a collection makes our code more intuitive and easier to extend. So, moving from individual variables to lists really enhances the design and maintainability of our classes. So, what happens if we try to store the circle objects using a list? Well, in our previous program, we created each pip with a line like self pip1 equals self. Make pip, cx, sci. Remember, makePip is a local method within the DieView class that generates a circle centered at the position specified by the parameters. Now, if we want to store multiple pips, One common idea is to use a list instead of individual variables. This leads us to consider designing with lists and classes, which can be very powerful. But there are some important points to keep in mind. When we use a list to store these circle objects, it allows us to manage and access them dynamically, especially if the number of pips or their positions might change. However, we need to be careful with how we create and update these objects within the list, making sure we handle each pip correctly. This approach ties into the overall theme of building more flexible and scalable code by leveraging lists and classes effectively. Let's explore one effective approach to building a list of pips. We start with an empty list, pips, and then add each pip individually. For example, we initialize pips as an empty list, and then we use the append method to add new pips, like self-make_pip with specific coordinates. This process continues, adding each pip one at a time, which provides us with precise control over the placement. Finally, we assign our complete list back to self-pips. This method highlights how using lists and classes together allows us to construct complex objects step by step, making our code more flexible and easier to manage. It's a practical example of designing with lists and classes to build our graphical elements systematically. Now, another straightforward approach is to create the list directly. Here, you can see that we assign to self-pips a list of objects, each created by calling the make_pip method with specific coordinates. Notice how the list spans multiple lines, with each pip created on its own line. Python is smart enough to understand that this list continues over several lines, as long as we include the closing square bracket at the end. This makes the code much more readable and organized, especially when dealing with multiple objects. Listing objects like this, one per line, helps us keep our code clean and easier to understand. It's a simple but powerful way to design with lists and classes, making our code clearer and more maintainable. Putting our pips into a list really makes many actions much simpler to perform. For example, if we want to blank out the die by setting all the pips to the background color, we can just loop through each pip in the list and set its fill to the background. This approach replaces what used to be a longer, more complex set of code. In fact, it cuts down what used to take 7 lines into just 2 lines. This is a great example of how designing with lists and classes can make our code cleaner, more efficient, and easier to manage. It highlights the power of organizing related objects into lists, which allows us to perform batch operations effortlessly. This concept is at the core of writing effective, modular Python code, especially when working with graphical objects like in our DICE project. Now we can turn the pips back on using the pips list. Our original code looked like this: self, pip1, set fills self foreground, self pip4, set fills self foreground, and self pip7, set fills self foreground. But instead of referencing each pip individually, we can simplify that by using the list. So it becomes self pips0, set fills self foreground, self pips3, set fills self foreground, and self pip6, set fills self foreground. This approach highlights how designing with lists and classes makes our code more efficient and easier to manage. It's a great example of leveraging data structures to improve clarity and scalability in our programs. Now, here's an even easier way to access those same methods. Instead of writing out each individual call, we can use a loop. For example, for I in brackets with 0, 3, and 6, we can set the fill color of self-pips at those indexes to the foreground color. This approach really streamlines our code. We can take advantage of this by keeping a list of which pips we want to activate. First, we might loop through all the pips to turn them off. Then, we determine the list of indexes for the pips we want to turn on. Finally, we loop through that list and turn on just those specific pips. This method really highlights the power of using lists and classes in Python. It makes our code more flexible, cleaner, and easier to manage. Overall, it's a great example of designing with lists and classes to make programming more efficient and organized. Let's take a closer look at this code snippet. First, we see a loop that goes through each pip in self-pips, and for each one, it sets the fill to the background color. This effectively clears or resets all the pips on the display. Next, the code checks the value variable, which represents a number, and based on that value, it determines which pips should be on or filled. For example, if the value is 1, only the pip at position 3 is turned on. If it's 2, then pips at positions 0 and 6 are turned on, and so on. As the number increases, more pips are lit up, mimicking the pattern of a digital number display. The key idea here is that we're controlling which pips are active based on the number we want to display. The list called on contains the indices of the pips that should be filled. Then, in the final loop, we set the fill color of those specific pips to the foreground color, making them visible. This approach highlights how lists and classes can be used to efficiently manage graphical elements, like these pips. It also demonstrates how clear logic can be applied to control visual output, which is essential in designing user interfaces or visual representations in programming. Overall, this code is a great example of how to use lists to manage multiple objects, and how to use conditional logic to control visual states dynamically, making the display adaptable to different numbers. We can do even better. The correct set of pips is determined by value. We can make this process table-driven instead. Instead of hard-coding each pattern, we can use a list where each item is itself a list of pip indexes. For example, the item in position 3 should be the list 0, 3, 6, since these are the pips that need to be turned on to show a value of 3. This approach makes our code more flexible and easier to maintain, especially if we want to change or expand the patterns later. By designing with lists and classes, we're leveraging Python's strengths to create a more efficient and organized way to handle these display patterns. Now let's take a closer look at this table-driven code. Here, onTable is a list of lists, where each inner list contains indices that correspond to specific pips. Essentially, it acts as a lookup table that tells us which pips to turn on or off based on the current value. In the loop, we first set each pip's fill color to the background, effectively turning them off. Then, we retrieve the list of indices for the current value from onTable. For each index in that list, we set the corresponding pip's fill color to the foreground, turning it on. This approach makes the code very flexible and easy to update, because instead of writing multiple conditionals, we just modify the lookup table. It's a great example of designing with lists and classes, using data structures to control visual elements dynamically. This method keeps the code clean and aligns with the overall theme of making our programs more modular and maintainable. Let's take a closer look at this code snippet. We start with onTable, which is a list of lists. Each sublist corresponds to a specific value, representing which pips should be lit up for that value. Notice that the first element is an empty list, which is just a placeholder since 0 isn't used in dice faces. This setup is important because it allows us to quickly reference which pips to activate based on the die roll. The comment here explains that this table remains constant throughout the lifetime of the die view, meaning we should store it in the constructor and keep it as an instance variable for efficiency. This way, we avoid recreating the table each time we update the display. Now moving to the loop. For each pip in self-pips, we first set its fill color to the background color. This effectively turns all pips off initially. Then, we look up the current values list in onTable, which tells us exactly which pips need to be turned on. We iterate through this list and set those specific pips to the foreground color, lighting them up. This approach is a simple and effective way to update the die face dynamically. By predefining the onTable, we streamline the process of activating the correct pips for each role, making the code both clean and efficient. It's a great example of how designing with lists and classes allows us to manage visual components in a clear, organized way. Let's take a closer look at how this class creates a visual representation of a die. First, it makes 7 circles, which we call pips, positioned at standard locations for each die face. These positions are calculated relative to the center, with an offset to ensure proper spacing. Each pip is created using a helper method, makePip, which draws a circle at the specified coordinates. Next, there's a table called onTable that defines which pips should be lit up for each possible die value from 1 to 6. For example, when the die shows a 3, pips at positions 2, 3, and 4 are turned on, matching the standard dot pattern. The set value method is key here. It first turns all pips off by setting their fill color to the background color. Then, it references the on table to identify which pips need to be turned on for the current die value and updates their fill color accordingly. This approach makes it simple to display any number from 1 to 6 visually. By organizing the pips into lists and using a table to map values to patterns, this design simplifies the process of updating the die face. It's a clear example of how using lists and classes can make your code more modular and easier to manage, especially in graphical applications like this. Lastly, this example really highlights the advantages of encapsulation. What we've done here is improve the implementation of the DieView class, but importantly, we haven't changed the set of methods it supports. This means we can replace this new version of the class seamlessly, without needing to modify any other code that depends on it. Encapsulation, in this context, allows us to build complex software systems as a set of pluggable modules. It keeps each part self-contained and manageable, making our code more flexible and easier to maintain. This is a key concept in designing with lists and classes because it promotes modularity and reduces the risk of unintended side effects when making updates. Now, the new DieView class really illustrates how lists can be used effectively as instance variables within objects. For example, our pips list and onTable are both collections of circles and lists, respectively, and importantly, these are objects themselves. This highlights a key concept. A program can be viewed as a collection of data structures, which include collections and objects, along with algorithms that operate on those data structures. This approach makes our programs more organized and modular. As we see in this case study of a Python calculator, understanding how data structures and objects work together is fundamental to designing effective programs. Let's develop a program that implements a Python calculator. Our calculator will feature buttons for the 10 digits, from 0 to 9, allowing us to easily input numbers. It will also have a decimal point button, so we can handle fractional numbers. To perform operations, we'll include the 4 basic arithmetic operators: addition, subtraction, multiplication, and division. In addition, there are a few special keys to improve usability. The C key will clear the display, giving us a fresh start for new calculations. The key acts as a backspace, letting us correct input mistakes without starting over. And of course, the equals key will execute the calculation based on the input we've entered. To organize this functionality, we'll think of the calculator as an object, a self-contained unit that manages its own state and behavior. This object-oriented approach makes our code more modular, reusable, and easier to maintain. By the end of this, you'll see how designing a calculator as an object aligns with good programming practices, and how it fits into the broader theme of creating interactive, user-friendly applications with Python. Today, I want to talk about thinking of a calculator as an object. When we look at this concept, we're really emphasizing how a calculator isn't just a simple tool, but a programmatic object that has properties and behaviors. By treating it as an object, we can better understand how to design software that mimics real-world devices. This idea ties into the overall theme of our presentation, understanding how to model real-world entities using objects in programming. So, in essence, a calculator can be seen as an object with attributes like current value, memory, and methods such as add, subtract, multiply, and divide. Recognizing this helps us build more modular, intuitive code, mirroring how we think about physical objects in the real world. Now let's look at a simple way to perform calculations in our program. As you press the buttons, each one appears on the display. Then, when you press the equals button, the expression is evaluated and the result is shown. This approach makes the process clear and straightforward. We can think of the calculator's operation in 2 main parts. First, creating the user interface, which includes the buttons and display. And second, handling the interaction with the user, like capturing button presses and updating the display accordingly. This is a perfect example of how we can structure objects in Python. By treating the calculator as an object, we can encapsulate its data and behavior, making our code more organized and reusable. It also aligns with our overall theme of designing modular, object-oriented programs. First, we create a graphics window, which serves as the main canvas for our calculator interface. The coordinates we choose are important because they help us simplify the layout of the buttons, making it easier to position them precisely. In the last line of this code, we store the window object in an instance variable self.win. This allows other methods within our class to easily refer to the same window, ensuring consistency throughout the program. By setting up the window this way, we're laying a solid foundation for building an intuitive and well-organized user interface. All right, now that we've set up our button creation, the next step is to create the buttons themselves, and we do this by reusing the button class we've defined earlier. First, we prepare a list called bspecs, which contains the specifications for each button. This list includes the center coordinates and the label for each button, making it easy to position and identify them. For example, you'll notice the standard-sized buttons like 0, 1, 2, 3, and so on, each with specific center points. The list also includes special buttons like the plus, minus, multiply, divide, and the clear button. We initialize an empty list called self-buttons, which will hold all our button objects. Then, we loop through each specification in bspecs, unpacking the center coordinates and label. For each, we create a button object, passing in the window, the center point, width and height, and label. These buttons are then appended to our self-buttons list. After creating all the standard buttons, we add the larger equals button. This button spans more space, so we create it with a wider width, specifically 1.75 units, and position it at the appropriate place. Finally, we activate all the buttons in our list, making them ready for user interaction. By reusing the button class and systematically defining each button's specs, we keep our code organized and scalable, an essential practice when building user interfaces. Now let's talk about how each specification is actually a tuple. A tuple, as you might know, looks very similar to a list, but the key difference is that it uses parentheses, or instead of square brackets. This subtle change is important because it tells Python that this sequence is a tuple. Tuples are sequences, just like lists, but they are immutable. That means once you create a tuple, you can't change or modify its contents. This immutability can be very useful in programming when you want to ensure that certain data remains constant and isn't accidentally altered later on. Understanding this concept is crucial as we move forward because tuples are often used in situations where fixed data is needed, or when you want to prevent accidental modifications. Recognizing when to use a tuple instead of a list can help make your code more reliable and easier to manage. So, in summary, each specification being a tuple emphasizes the importance of immutable sequences in Python, and knowing how to construct and work with them is a key part of developing robust interfaces. All right, let's break down what's happening in this part of the code. Conceptually, each time we go through the loop, we start with an assignment. CX, sci, label equals the next item from bspecs. Now, each item in bspecs is itself a tuple, which makes things pretty straightforward. When we assign a tuple to variables on the left side, Python unpacks the tuple's components directly into those variables. So, for example, on the very first iteration, it's as if we had CX, sci, label equals 2, 1, and 0. This unpacking process is key because it allows us to handle multiple related pieces of data efficiently, all in one go. And this pattern repeats every time through the loop, always pulling the next tuple from bspecs and unpacking it into our variables. This is a clean way to process structured data like this, especially when dealing with interface elements or specifications, because it keeps the code concise and intuitive. It's really about making the relationship between your data and your variables as clear as possible, which is essential for building robust, maintainable programs. All right, so as we go through each iteration of the loop, we're unpacking a tuple from bspecs into the variables defined in the loop header. This means that for each tuple, its values are assigned to specific variables, making it easy to use those values right away. Once we have those variables, we use them to create a button object. This button is then added to our list of buttons, which helps us manage and display multiple buttons efficiently. When it comes to creating the display itself, it's pretty straightforward. We draw a rectangle, and then we place some text centered on it. An important detail here is that we save the text object as an instance variable. Why? Because later on, we might need to access or modify that text, so storing it as an instance variable makes that possible. In summary, this process of unpacking, creating buttons, and managing text objects is fundamental to building a dynamic and interactive interface in our program. Now, let's take a closer look at the code used to create the display. First, we define a rectangle called BG, which serves as the background for our text. We set its position using 2 points, the lower left corner at 0.5, 5.5, and the upper right corner at 5.5, 6.5. Then, we fill this rectangle with white color to make sure our text stands out clearly against the background. After setting the fill, we draw the rectangle onto the window. Next, we create a text object called text, positioned at the point 3, 6. Initially, it's empty, but this is where our message will appear. We draw this text object onto the window as well. To make the text visually appealing and consistent, we customize its font to Courier, set it to bold style, and choose a size of 16 points. Finally, we assign this text object to self-display, which allows us to update or modify the displayed message easily later on. This setup is fundamental because it creates a clear, styled area for dynamic messages in our interface, tying into the overall theme of building user-friendly graphical interfaces in Python. Now that the interface is drawn, we need a method to get it running. We'll use an event loop that waits for a button to be clicked and then processes that button. The run method essentially keeps the program running indefinitely, constantly listening for user input. Inside this loop, we call getButton to check which button, if any, has been pressed. Once we have that information, we pass it to processButton to handle the specific action associated with that button. This approach is fundamental to interactive applications because it allows the program to respond dynamically to user actions. By continuously looping and processing input, we ensure our interface remains responsive and functional throughout its operation. So, what we're doing here is continuously checking for mouse clicks until a button is actually clicked. The idea is to keep looping, waiting patiently for the user to interact. To determine if a button has been clicked, we go through our list of buttons one by one and check each one individually. In the code, there's a method called getButton, which essentially waits for a mouse click event. When a click occurs, it captures the position with getMouse. Then, it scans through all the buttons to see if the click was inside any of them. If it finds a button that was clicked, it immediately returns the label of that button. This way, we know exactly which button the user pressed, and we can respond accordingly. This process is crucial because it highlights how we handle user interactions in graphical interfaces, by constantly listening for input and then processing it in an organized way. It's a fundamental concept in event-driven programming and really ties into the overall theme of making our programs responsive and user-friendly. Having the buttons organized in a list like this is a real win for our code. It makes it much easier to handle multiple buttons without writing repetitive code. By using a for loop, we can go through each button one by one, which simplifies the process significantly. Now the key part here is checking if the point P, which is where the user clicks, falls inside any of these buttons. If it does, we want to identify which button was clicked. So inside the loop, we test whether P is within the current button's area. And here's the clever bit. If we find that P is in a button, we return that button's label. This gives us a quick way to know exactly what was clicked, and importantly, it allows us to break out of the loop immediately. That prevents unnecessary checks once we've found our answer. This approach exemplifies how loops and conditionals work together efficiently. It's a fundamental strategy in programming that makes our code cleaner, faster, and more maintainable. It's a perfect example of turning a potentially complex problem into a simple, elegant solution. The last step in our calculator program is to update its display based on which button was clicked. Essentially, When a user presses a digit or an operator, we want that input to appear on the screen. To do this, we append the new character to the existing display content. If the button has a label, which is stored in the variable key, and the current display is stored in text, then the code to update the display is simply self-display, set text and text plus key. This line takes the current display, adds the new input, and updates what the user sees. This process is fundamental because it ensures that each user action is reflected immediately, keeping the calculator responsive and intuitive. Connecting this to our overall theme, it highlights how user interaction is handled seamlessly through simple, clear code, making the calculator both functional and user-friendly. Now let's look at some key buttons and how they work in our simple calculator interface. First, the clear key, which is quite straightforward. It resets the display by setting the text to an empty string. So when you press clear, the display is blank again, ready for new input. Next, the backspace key is a little more interactive. It strips off one character at a time from the end of whatever's currently displayed. This is done by slicing the text, specifically using text -1, which means all the characters except the last one. It's a handy way to correct mistakes without clearing everything. And finally, the equal key. This is the moment where the magic happens. When you press it, the expression you've entered is evaluated, meaning Python calculates the result, and then that result is displayed on the screen. This ties everything together, showing the output of your calculations. These buttons are fundamental because they manage user input and output in a way that's intuitive and responsive, which is at the core of creating a user-friendly calculator. They demonstrate how we can connect user actions to Python functions seamlessly, reinforcing the overall theme of building interactive programs. Now, let's take a look at this code snippet. Here, we're using a try and except block to handle potential errors that might occur when evaluating text as a Python expression. The line result equals evaled text attempts to execute the code contained in the variable text. If this code runs successfully, the result will store the output of that evaluation. However, if there's an error, say if the text isn't a valid Python expression, the except block will catch that error. Instead of crashing the program, we assign the string error to result. Then, we update the display with this message, ensuring the program continues to run smoothly. This concept of exception handling is crucial because it makes our programs more robust. It allows us to anticipate and manage runtime errors gracefully. In this context, it ensures that if a user inputs an invalid expression, the program won't crash but will instead inform the user that an error occurred. This is a key aspect of writing reliable and user-friendly software, especially when dealing with dynamic inputs or code evaluation. It ties back to our overall theme of writing resilient Python programs that can handle unexpected situations without breaking down.